On April 13, 2026, the Wolf River in northern Wisconsin crested at 13 feet. Not during a named storm, not during any recognized large-scale weather event. Just an ordinary April Monday. And it didn't climb alone. By the end of that same day, a magnitude 5.5 had rolled through Nevada. A wildfire was consuming 1,200 acres of subtropical Florida, and 14 severe weather warnings were active across the upper Midwest simultaneously. Yesterday's events weren't a collection of isolated incidents. They were a single, coherent signal, and this is what it was telling us. That number, 13 feet, is the kind of data point that gets buried in the third paragraph of a local news brief, sandwiched between a school board meeting recap and a used car dealership advertisement. But if you know how to read what that number is telling you, if you understand what had to happen atmospherically for a river in Wisconsin to behave that way on April 13th, 2026, then you start to understand that yesterday wasn't a collection of isolated weather events. It was a single, coherent signal, a stress test, and the country failed it in several places simultaneously. We're going to walk through all of it, slowly, methodically, because the pieces connect in ways that the standard broadcast rundown simply doesn't have the patience to explain, and by the time we get to the end of this, to the part where we talk about what was happening in the ground beneath Nevada at exactly 6:30 in the evening, you're going to look back at that Wisconsin River and understand it differently. So let's start with the air itself. By mid-April, the central and upper Midwest is essentially a thermodynamic pressure cooker waiting for a lid to come off. All winter long, cold air masses have been draped across the region, suppressing convection, keeping the atmosphere stable and layered. Then spring arrives, not gently, not gradually, but as a collision. Warm, moisture-laden air pushing north from the Gulf of Mexico slams into the remnant cold air, still anchored across the northern states. And when those two air masses meet, especially under the right upper-level wind conditions, the atmosphere becomes extraordinarily unstable. That instability has a name: convective available potential energy, CAPE. And yesterday the CAPE values across Minnesota, Wisconsin, Iowa and Michigan were not subtle. They were the kind of readings that make experienced meteorologists stop talking and start watching radar closely. Now here's what most people don't appreciate about CAPE. It isn't just a measure of how violent a storm can become, it's a measure of how much energy the atmosphere has been quietly accumulating, storing it, essentially, like a compressed spring. The higher the CAPE, the more violent the release when the atmosphere finally convects. And yesterday, that release came in the form of supercell thunderstorms, multiple, organized, moving with purpose. 14 active severe weather warnings across the region, a 10% tornado probability from the Storm Prediction Center, which sounds modest until you understand what that number actually represents when you're talking about a regional outbreak rather than a single isolated storm. Supercells developing in Minnesota, tracking southeast through Wisconsin, interacting with lower-level moisture pooling across Iowa, storm clusters rotating and reorganizing across the Great Lakes corridor into Michigan. And within that outbreak, a couple of possible tornadoes. The word possible is doing a lot of work there, and I want to be careful about it. The Storm Prediction Center doesn't use that language carelessly. What it tells us is that at least 2 supercells produced rotation signatures significant enough to generate tornadic activity, likely in the EF2 range or approaching it. EF2 means winds between 111 and 135 miles per hour. It means a well-built frame house loses its roof. It means vehicles become projectiles. It means the difference between a frightening story someone tells later and an outcome they don't recover from can be measured in a few hundred yards of ground track. But the tornadoes, as alarming as they are, were not even the primary hazard yesterday. And that fact alone tells you something important about the scale of what was occurring. The hail was baseball-size hail, 3 inches in diameter, falling from supercell updrafts across the upper Mississippi Valley. I want you to think about what it physically takes to produce a hailstone the size of a baseball. The updraft inside that thunderstorm, the column of air rushing upward from the surface into the storm, has to be strong enough and sustained enough to keep a growing ice pellet aloft for an extended period. The National Severe Storms Laboratory estimates that producing baseball-size hail requires updraft speeds of approximately 100 miles per hour or more. Inside the storm, Not the wind you feel on the ground, the vertical wind inside the thunderstorm's core. The 30% hail probability that the Storm Prediction Center posted for this region wasn't a warning about inconvenience. It was a warning about structural damage. Baseball-size hail destroys crops at a time of year when fields are being prepared for planting. It tears through roofing materials, vehicle glass, greenhouse structures. It creates insurance claims that ripple through local economies for months. And it tells us something about the vertical wind shear in the atmosphere, the change in wind speed and direction with altitude, that made yesterday's storm so structurally intense. Wind shear is what organizes a thunderstorm. Without it, convective cells rise, rain out, and collapse. With it, the storm tilts, the updraft and downdraft separate spatially, and the storm becomes self-sustaining. Yesterday's wind shear profiles across the upper Midwest were textbook for organized long-track supercell development. The atmosphere was configured almost perfectly for producing exactly what it produced. And then those same storms, the ones producing baseball hail and possible tornadoes, also produce straight-line wind gusts between 60 and 75 miles per hour. Downdraft-driven winds. When the precipitation core of a supercell descends, it drags cold air down with it, and that air accelerates outward when it hits the ground. 75 miles per hour is not a curiosity. That is equivalent to a Category 1 hurricane wind speed. Sustained, that kind of wind brings down power lines, snaps mature trees, tears the faces off barns, and blocks roads with debris for hours. Now, here's where the compounding starts, and I want you to follow this carefully because this is the part that exposes the real stress on the system. All of that precipitation, the heavy rain embedded in those supercells, the rain that preceded the hail cores, the rain that followed the downdraft passages, all of that water had to go somewhere. The soil across the upper Midwest in April is not fully thawed everywhere. Snowmelt from earlier in the season has already saturated portions of the drainage basins, and when you lay a significant convective rainfall on top of ground that cannot absorb it efficiently, you get runoff. Rapid, aggressive runoff. The Muskegon River in Michigan approached major flood stage. The Wolf River in Wisconsin climbed to around 13 feet. Those aren't simultaneous coincidences. Those are the same storm system expressing itself across a river network that spans hundreds of miles, each basin responding to the same precipitation event with a slight temporal delay as the runoff consolidates and moves downstream. And here is the part that I find genuinely troubling about yesterday. Not because flooding hasn't happened before, not because supercells are unusual in April, they're not, but because of the simultaneity of it all. 14 severe weather warnings, flash flood concerns, rivers approaching major flood stage, all at the same time, in the same region. Which means every emergency management office, every county coordinator, every 911 dispatch center across that corridor was being asked to manage multiple, distinct, overlapping situations simultaneously. Tornadoes and floods don't wait for each other. They don't give emergency responders the courtesy of arriving sequentially. That's where systems break. Not at the point of the major disruption itself, but at the point where the response capacity is overwhelmed by concurrent demands. I mentioned that we'd come back to something. Hold that thought, because we're not done with the picture yet, not by a long measure. While all of this was occurring in the upper Midwest, while the rivers were climbing and the hail was falling and the wind was doing 70 miles per hour across Wisconsin cornfields, Kansas was sitting under a completely different threat. Not water, fire. A fire weather watch covered portions of western Kansas on the same day. Greeley County, Wichita County. Warm temperatures, low relative humidity, breezy southwest winds. The conditions required for rapid fire spread. No rain, no severe storms, just the dry, warm side of the same synoptic system that was pumping Gulf moisture into the storm environment to the north. This is the thing about large-scale weather patterns that doesn't get communicated clearly. A single mid-latitude cyclone, a low-pressure system tracking across the central United States, doesn't produce one type of weather. It produces a spectrum. The warm sector ahead of the cold front is warm, moist, and unstable. That's the tornado and hail and flood territory. The area behind the cold front, especially across the elevated terrain of the high plains, gets the dry air, the low relative humidity, the winds, and the fire risk. So you have, on the same day, in the same country, fire weather watches in Kansas and flash flood warnings in Wisconsin. That's not a contradiction. That's physics. That's how a mid-latitude cyclone works. But it's also a resource allocation problem. Fire suppression assets, aerial support, hotshot crews, those resources are finite. They can't be in two places at once. And while Kansas was dry and susceptible, Florida was burning. The Picayune Strand wildfire in Collier County, Newman Drive, was at 1,200 acres yesterday with 15% containment. Evacuations ordered. This is southwest Florida, subtropical ecosystem, dense cypress swamps and pine flatwoods that are normally wet enough to resist extreme fire behavior. But fuel moisture deficits, the drying out of vegetation that normally retains enough moisture to resist ignition, have been building. And once a fire establishes itself in that kind of landscape, the natural fire breaks that you'd expect to find simply aren't functioning the way they should. 15% containment on 1,200 acres means the fire is largely doing what it wants. Firefighters are working the edges, trying to construct lines, but the interior is active, and with evacuations ordered, you have communities displaced, families uncertain about whether their homes will still be standing when they are allowed to return. 1,200 acres in Florida, fire weather watch in Kansas, flash floods in Wisconsin, tornadoes in Minnesota, all of this, yesterday. Now I want to talk about the East Coast for a moment because the heat that was building there adds another dimension to this picture that I think gets overlooked. Record or near record high temperatures in April, we're talking 80s and 90s along the East Coast from Atlanta north toward Washington, represent anomalous early season ridging. A high pressure dome anchored over the Atlantic, pumping warm air northward ahead of schedule. April records threatened in cities that typically see those temperatures in June. That ridge is not just a heat story. That ridge is the same upper-level atmospheric configuration that was directing the storm track across the Midwest. High pressure to the east, low pressure digging from the northwest. The gradient between them is what was driving the severe weather corridor. The heat on the East Coast and the tornadoes in Minnesota are different expressions of the same synoptic scale atmospheric setup. But the heat matters on its own terms too. Early season heat events stress power grids. People who weren't expecting to run air conditioning in mid-April are running air conditioning. Elderly individuals living alone in homes not yet configured for summer cooling face genuine health risk when temperatures reach the 90s. The agricultural sector faces early soil moisture evaporation before crops are even in the ground, and perhaps most critically, that heat is building atmospheric energy. The same anomalous warmth that's threatening records on the East Coast is contributing to the thermodynamic instability in the Midwest. Warm air aloft being overridden by cold air from Canada, that's fuel. That's the atmosphere loading the spring. Now, and I said we'd come back to this, Nevada. At approximately 6:30 in the evening on April 13th, 2026, the ground moved near Silver Springs, Nevada. Magnitude 5.5, depth of 8 miles, 13 kilometers, shallow, which means the energy radiated outward efficiently rather than being absorbed by deep rock before it reached the surface. Hundreds of thousands of people felt it. Silver Springs sits in the Basin and Range province, one of the most seismically complex landscapes in North America. The Basin and Range is a region that has been literally pulling apart for tens of millions of years, the crust stretching and thinning under extensional tectonic forces, creating a series of parallel fault-bounded mountain ranges and intervening valleys. The faults in this system are numerous, many of them capable of generating significant seismic events, and many of them relatively understudied compared to the more famous California systems. A magnitude 5.5 at 8 miles depth is not a minor curiosity. It's a substantial seismic event. It came with aftershocks, multiple, which tells us the fault system is still adjusting, still releasing accumulated strain, and because the crust in this region is relatively thin and the fault geometry is complex, the aftershock sequence can extend for days or weeks. Now I need to be precise about something here. There is no scientifically established mechanism by which a thunderstorm outbreak in Wisconsin directly triggers an earthquake in Nevada. I'm not going to tell you there is. What I'm going to tell you is this. On April 13th, 2026, the United States experienced a major severe weather outbreak with possible tornadoes in the upper Midwest. Baseball-size hail, hurricane-force wind gusts flooding rivers, a wildfire burning out of control in Florida, fire weather conditions across Kansas, record heat threatening the East Coast, and a magnitude 5.5 earthquake in Nevada, all in the same 24-hour window. The significance of that is not the meteorology causing the seismology. The significance is the systemic exposure of a country to simultaneous, geographically distributed hazards that demand simultaneous, geographically distributed responses. Emergency management, FEMA, state and local resources, medical systems, utility infrastructure, all of it stressed concurrently. That is the actual story. That's the risk model that doesn't get talked about enough. There was also a minor G1 geomagnetic storm, KP index around 5, occurring simultaneously. Minor, yes, but worth noting in the context of infrastructure sensitivity. Power grids already strained by early season heat demand, already dealing with storm damage to transmission infrastructure in the Midwest, also sitting under elevated geomagnetic activity. G1 is not an extreme scale event, but it's another variable, another stressor layered on top of an already taxed system. What concerns me about yesterday, and what should concern anyone thinking carefully about resilience and vulnerability, is the trend. Not this single day in isolation, the trend. These compound event days, days where multiple distinct hazard types occur simultaneously across multiple regions, are not random accidents. They are the result of a thermodynamic environment that is becoming more energetically loaded, springs that arrive faster and more violently, temperature gradients that are sharper, storm systems that are more intense in their hazardous outputs. The Muskegon River approaching major flood stage in April tells you the watershed was already primed, antecedent soil moisture, remnant snowpack, and then this convective deluge on top of it. The fuel moisture deficit sustaining a wildfire in a subtropical Florida swamp tells you the seasonal drying patterns have shifted. The April heat records threatening Washington and Atlanta tell you the seasonal temperature progression is no longer following historical norms. None of these things is, by itself, a declaration that the sky is permanently broken, but together, across a single calendar day, they describe a country operating at the edge of its response capacity with a hazard environment that continues to intensify. The rivers in Wisconsin will recede. The wildfire in Florida will eventually be contained. The earthquake aftershocks in Nevada will quiet. The heat records will be broken, or they won't, and by June we'll have moved on to the next cycle. But the underlying conditions, the atmospheric energy loading, the drought-driven fuel buildup, the tectonic strain accumulating along basin and range faults, those don't reset overnight. They continue building between events. So the question I want to leave you with today is this. When you watch the local news give you the 60-second weather hit and the 30-second earthquake mention and the scroll about the Florida fire, do you feel like you understand what actually happened yesterday? Because I'd argue you don't. Not from that. Not from the fragmented version. If this kind of systematic, unhurried analysis is what you're looking for, the kind that takes the scattered data points and maps the actual connections between them, then subscribe. Not because some algorithm needs the number, but because this is what vigilance looks like. Watching these patterns, tracking these trends, refusing to accept that 14 severe weather warnings and a flooding river and a Kansas fire watch and a Nevada earthquake are just coincidentally loud background noise. They're not noise, they're signal, and you owe it to yourself to learn how to read it. Hit the like button if this gave you something to think about and tell me in the comments. What do you think was the most underreported hazard from April 13th? The tornadoes? The hail damage? The Florida fire with 15% containment? Or is there something about that Nevada earthquake, that shallow 5.5 with aftershock still rolling through the basin and range, that you think deserves a harder look? I'll be back when the next set of data gives us something worth examining carefully, and lately, the data always does.